Hello, my name is Stacy, and I'll be talking about topological sort in this final presentation video. Topological sort in a directed acyclic graph is one of the applications of the graph search algorithms. Before I go into the topological sort, we should understand what a directed acyclic graph is, because without the directed acyclic graph, there's no topological sort. So what is an acyclic graph? And what does it mean by a directed acyclic graph? Acyclic graph is a graph that doesn't have any cycles, so this means there's no path for information to return to the nodes without doubling back and hitting the nodes that have already been encountered, since there is no cycle. And the directed acyclic graph is the same as the acyclic graph, except it has directed edges. Topological sort gives a linear ordering of vertices in a directed acyclic graph, so that for every directed edge, A pointing to B, vertex A comes before vertex B in the ordering. In other words, the topological sort returns an array of the ordered nodes, where each node appears before all the nodes it points to. The runtime of the topological sorting algorithms is usually linear in the number of nodes plus the number of edges, like O of V plus E. In the later slides, I'll go over some specific algorithms for topological sorting, such as Kahn's algorithm. In this slide, I'll be talking about properties of topological sort. Topological sort can have certain properties that act as constraints on the input or the output. As I briefly introduced before, the most important foundation of the topological sort is the linear ordering of the vertices in a directed acyclic graph, having the property that every vertex V in the respective ordering occurs before any other vertex to which it has edges. To simplify this concept, I'll call this property as dependencies. Given the edge from A to B, A must be completed before B can be started. For example, at the University of Arizona, the computer science students must take CSC 120 before 210 and 210 before 335, etc. This kind of prerequisite condition is found in the topological sort as well. A directed acyclic graph has at least one vertex with an in degree of 0 and one vertex with an out degree of 0. It must have at least one vertex that does not have any incoming edge. This is very important because we set the first vertex of the topological sort as the vertex with an in degree of 0. Another property we should know is that we can use topological sort if and only if the graph is acyclic. Edges on a cyclic graph can't be removed for linear ordering because of the cyclic edges between two or more vertices. In this example graph that I drew, node 1 is pointing to nodes 2 and 3. So as you can see, node 1 appears first in my result array here. Node 2 and 3 are pointing to node 4. Node 2 and 4 are pointing to node 5. So in the linear order, it can be listed as 1, 2, 3, 4, 5, but it's not limited to one topological sort order because it can also be 1, 3, 2, 4, 5. Now let's study the design of the topological sort. Here we will observe the details of Kahn's algorithm developed by Arthur Kahn in 1962. This is used to perform a topological sort on a directed acyclic graph with the time complexity of O of V plus E, like we talked about in the previous slide, where V represents the number of vertices and E represents the number of edges in the graph. For Kahn's algorithm, we need an array to hold temporary results of the pre-processing stage, and we also need an int variable to store the number of visited vertices. We can set a string or another array to hold the results. which will be used to store the new topological order, and then we also need a queue. First, we enqueue the vertex that has an in degree of 0. While the queue is not empty, we dequeue the vertex, add this vertex to the result array or string, then we increment the int variable visited by 1. And we decrement the in degree of all its neighboring vertices by 1 in the temporary array. And then we can enqueue the neighboring vertices with the in degree of 0. If the value of the int variable visited is equal to the number of vertices in the graph, then we know it's finished, and then the result array will contain the topological sort for the graph. Now, let's review how the topological sort works in greater detail. I think it always helps me to draw the graph and go over every single step when it comes to understanding complicated algorithms. So here I made a pretty basic animated video to demo how to do step-by-step of topological sort. As you can see, for this directed acyclic graph, we're going to look for a node that doesn't have any incoming directed edges, which is A in this case. So I'm setting that as the first node, and I'm going to add A into our topological ordering. Now, I'm doing the same thing with E. So once a node is added to the topological ordering, we can take the node and then its outgoing edges out of the graph. So I'm just removing this node. And then we just repeat this approach by looking for any node with an in degree of 0. In this case, this is B. So we do it over and over again and add it to the ordering. And then we just repeat this process until we run out of the nodes. This is not the only way to produce a topological ordering, but personally, I find this method to be the easiest and also very easy to implement. And then we have it. Now we're going to move on to implementation. Let's take a look at this Java implementation. We have a class graph to represent a graph here, and I am setting the int v, and this will represent the number of vertices in a given graph. And there's a list that contains the references to the adjacency list of each vertex. We are defining the constructor here, and we're moving on to this add edge method that will add an edge to the graph. On the right side here, we can see the topological sort method, and here we are setting up an array, integer array, to store in degrees of all vertices. Next, in the nested for loop, we traverse the adjacency list to fill the in degrees of vertices. Just like the previous algorithm design slide, we are going to use a queue, and we're going to collect the vertices with in degrees of 0 by using enqueue. And then we want to keep track of how many nodes we already visited. So we are initializing an int variable, int count here, and setting it to 0 before the while loop. So while the queue is not empty, we are going to iterate through all its neighboring nodes of the dequeued node and decrement their in degrees by 1. And after this process, we can use a for each loop to print the topological order. Moving on to application and future work, Topological sorting can be used in a lot of different scenarios that involve scheduling a number of tasks that have interdependencies. When we create a number of database tables, and when it becomes really complex, some tables will have interdependencies, and we can use topological sort to determine the order in which we create them. Another real-life application example is the course prerequisites. Like I mentioned before, most university degrees require completion of the prerequisite courses, and we can use topological sort to solve this. Doing laundry is also another application of topological sort because we need to wash the clothes before we can dry them, and we need to complete the step of drying the clothes before we can fold them. So, simple things like laundry is also an application of topological sorting algorithm. And if you used Node.js before, you're probably familiar with the NPN dependencies. This is also another real-life application example. And in the future, we can consider ways to improve the time complexity of the topological sorting algorithms. And since most of the time there's more than one topological order, we could consider ways to improve the accuracy of scheduling decisions as well. We can also use topological sort to improve sentence ordering with sequence prediction. This technique has its own limitations and constraints, so this is something we can consider to improve in the future as well. In this presentation, we discussed about what topological sort is. We also reviewed the properties, the dependencies, and the conditions of directed acyclic graph. And we reviewed Kahn's algorithm, the algorithm design, and I demonstrated how it works through the step-by-step illustration. We also looked at the Java implementation of topological sort, and we learned about the real-life application examples and how topological sort can be improved in the future works. Thank you for watching my presentation.